faculty members, research scholars, and my friends. So today I will present my registration seminar titled on development of advanced VOC gas sensor for the early disease diagnosis and environmental air quality monitoring. So in our lab, we have a legacy to work on gas sensors. So plenty of papers have been published and plenty of Ph.Ds are worked on the gas sensor. But why do we need gas sensor? So most of us are aware of the gas sensor, what is gas sensor. But during my the registration presentation, I will explain why do we need advanced VOC gas sensor, the application, what is gas sensor, the brief idea, type of gas sensor reported in the literature. Then why do we choose a specific type of sensor? Why I choose class of materials which is TMDCs, which is suitable for my gas sensing. Research gap and literature survey. The brief history actually from the classes of Lahiri sir, I have seen he actually mix the theory, not only the theory part with but the insight of the scientist and the brief history. So a brief history, what's the pioneer of this field think about and observe about the gas sensor, and they establish some theories. The problem statement, the research objective, division of work, and the primary results of my experiments. So the first is, why do we need advanced VOC gas sensor? So gas sensor have vast application in a field of automobile, in a field of health hazards and safety, industries, so many applications. But slowly it's also have a application in a field of bioelectronics or bio sensing, because a human body continuously release the VOC gases through breath, through smell, through skin, through sweat, and the bodily fluids. So by the specific amount, the VOC can, if we can develop the sensor to detect it, we can identify all the identify the disease from this biomarker. So that's the need of the advanced VOC gas sensors. So this is the basically disease I just list down, and VOCs attached to that. For the lung cancer, formaldehyde and aldehyde, diabetes, for ethyl acetone, kidney and liver disorder, ammonia. So this is a brief idea of sensing. Gas sensor. A sensor is a device that detects change in an environment and outputs in a corresponding quantitative signal. So quantitative signal. So what's the characteristics of the gas sensor? It should be detects a specific gas, monitor the ambient gases. The gases are in mixture, so it should be selected or should be identify each type of gas. Then quantitatively translate the gas or solid interaction or gas or molecule interaction. So qualitatively, it should not quantitatively, it should not be the yes or no. It should be also tell you how much. So that's the more or less characteristics of a gas sensor, a brief idea of gas sensor. And what is the gas sensor present or the reported in literature? The first is optical sensor, MEMS sensor, electrochemical sensor, chemi-resistive sensor, MOSFET based sensor, and TFT based sensor. So optical, is a bulky, big, but accurate. It's difficult to it's difficult to compatible with the CMOS technology. So optical sensor, that's why I have chosen the TFT based sensor. Most of the sensors are not compatible with CMOS technology, fabrication technology. And the second part is high footprint, high area footprint. So MEMS sensor, it's also a very good for the specific gas detection. But in a case of multi-gas sensing, it may not be the correct option. So let's move to the TFT for the constraint of the time. So TFT, the architecture of TFT is very beautiful. It's upside down of the MOSFET. It's first gate, then oxide, then we have channel and contacts. So the channel is exposed to the ambient. So directly molecules can sit on the absorb on the channel, and it maybe modulate the different conductivity, density, VTH, anything. So this is a suitable, and fabrication wise is also easy. So TFT, then what would be the choice of selection of the materials? So TMDC or 2D base, after the 2010-2012, the graphene sheets are used as a FET, GFET, MOS2, SNS2. So many TMDC may arise, and it have a different vast application. The application of in application of paints and coatings, energy harvesting devices, biosensing, drug delivery, because it have a high surface to volume ratio, easy to fabricate. The third is very interesting. Band gap we can tune by the choosing of synthesis, different the synthesis parameters, temperature, pressure. We can tune the band gaps. So that's why we choose the TMDCs. So research gap. So most of the papers have been published which is based operate at a high temperature, 50 degree, 200 degree, 300 degrees. But for the hand handling device, for the good lab to industry as a product type of device, the guidelines is that 50 degree is the at most device operating temperature. So temperature is a constraint, and 90% papers are saying that we are our sensor is selectively detect this gas, but they are not sensing in a cross gas mechanism. 3 or 4 type of gases mixed together, and how their sensor is behaving, they are not claiming that. So if I want to make a VOC sensor which may detect the 4 or 5 VOCs, we need to connect like array. So for multiple gas sensing, I need to connect it in array form. So you can see the electrical signals line, lane 1, 2, 3, 4, and gates also. So many complex signal processing required, and that's why 90% papers are not giving the interfacing circuit. So if I able to make a single sensor which can detect the multiple VOCs, so our signal processing part is also optimized, or the cross gas sensitivity also we can check. So that recently no paper have been published on that, but when we go to the pioneers of this work, the first one is the father of quantum chemistry, Thomas Graham. He observed some certain thing. The first one is volatile. The gases behave like a volatile liquid, so that governing the the principles of liquid and solid interaction can be extended to the gases. So what we see in a liquid, we can apply on the gases also. The second, the different gases are absorbed in a varying amount on a single material. And the contradictory, the same gases may have the different affinity towards the different materials. So here we can check the multi-gas interaction. Single material can interact with other different gases. May or may not be the so many interactions are there because of electron affinity, but it's there. The third, when we heat the material, we can change the interaction between the solid and gas. So affinity, we can change the affinity. The fourth, if we have a certain structural parameters, lattice dimension, crystal structure, interstitial site, we have, but if we don't have the perfect matching electron affinity, the gas will not adsorb on the material. That means if we change the surface energy, if we modulate the surface energy, we can change the gases absorption and desorption mechanism. So at particular surface energy, a particular gas is attached and the other one is not. So by this principle, I would like to present my problem statement to develop a single scalable room temperature based platform sensor which is capable of which is capable of selective detection, discrimination, quantification at a real time with mixed gases, multiple gases, with the integrated with the signal processing interfacing circuit. So research objectives. First, I have to choose the material, and then at room temperature, I have to experiment with a multiple gases environment, single gas environment. Then quantification, created a database to apply the physics-based ML. So ML and AI is a hot topic nowadays, but the thing is, they're not backed by the physics. They just pattern recognition and design a low noise interfacing circuit. So this is the more or less. So this is the more or less work division. First, synthesis the material, then check in a multiple gases environment, and the thing is we are making the interdetailed electrodes. The architecture is same more or less by fabrication point of view, but I want to change or modulate the architecture wise things also. And again, the ML part, we have to maintain a database. We have to do the rigorous experiments to create a database which can be input in a ML. So interfacing circuit of these devices, and then these three. So these three, mass flow controller, chip packaging, product design, is basically, so previous 5 or 6 points are the focus on research part, and the third 3 points are the focus on product point of view. If we can present a product, so mass flow controller, why do we need mass flow controller on a gas sensor? But it should be integrated because different, we have almost 20 in this room. Different person have a different flow rate, blow rate, right? Of exhale, breath. So that may be the issue with the sensor. That may be alter the signals. So a mass flow controller should be sitting on the sensor. Then chip packaging, just like how we do the insulin checking or the diabetes checking. We have chip and we put the blood and check and product design. So this is my primary work. Gate tunable single silver graphene oxide, reduced graphene oxide PET platform for room temperature tri-gas detection. The CMOS compatible PWM readout circuit. There is a single sensor which is working on a room temperature, three gases detection, and also there is an interfacing circuit. So hypothesis.
What's PWM?
Pulse width modulation. So basically analog to digital. So
And try the gas simultaneously.
yeah. So this is a hypothesis. So Dr. Nimisha has worked on liquids or soil sensor ion detection basically. So she has seen when we sweep the voltage minus 15 to 15 at particular voltage, if the ion is present, it gives the maximum response at particular voltage, right? So irrespective of the it's mixing or not, it's present in a mixture or a single. So by the extend this idea to the gases, so she had done on the liquid. I want to perform it gases, and so first is device fabrication. Basically, we take the heavily doped silicon and oxidize by the oxidation 122 nanometer oxidation SiO2 growth, lithography, metallization, and then contacts. And this is a Hammer's method, which by GU and RGO is present, you can synthesize. So it's not normal, it's nothing normal in it. So that's the material characteristic. For the constraints of the time, I just want to skip that. The characterization of material is just to check the carbon, oxygen, and how in which oxidation state and which bonds are present in the material. So
What's figure E?
So this is a Raman. This is a FTIR.
Figure E.
Figure E. This is the EDEX. So the overall EDEX and the elemental mapping.
Like, what does E actually represent?
So each green point represents oxygen, and red point present it's not visible.
It's not visible.
Yeah, but C carbon 19%, Ag is 10%. So कितना percentage है in a material? So yes.
दिख रहा है?
Yeah, मतलब closely दिख रहा है. So इसका इसको change कैसे?
ठीक है, it's all right. Carry.
So yeah, the principle is same. If we sweep the minus V to V voltage, a particular gas absorb on the sides and give their response. So let us skip. So that's the result. So I just sweep minus 5 to 5 volt and take the transfer characteristic, the field effect transistor. So you can see this is lighter one in a logarithmic scale and the darker one in a normal scale. You can see there is not much change in the current. Same for the acetone, formaldehyde, and ammonia. But when we take the response delta I by I, when we normalize it, each gas at particular voltage, ammonia for the minus 1.8, formaldehyde for the minus 3.0, acetone for the minus 4.4, giving the response, giving a peak. So I first peak on it. The formaldehyde is a dip, and acetone and ammonia is a peak, depending on the it's giving the electron or taking the electron.
So you try to detect three gases, so formaldehyde and
yes,
ammonia.
Ammonia. So first I individually check, then second I take mixture. So suppose this is a purple one. So purple one have a peak 1.8, dip at 3.0, and there is a peak in 4.4. So all three are present. If one of them are absent, the peak or dip is not there. So that's actually three gases at a particular time. Then I choose that might be the okay peak aa raha hai ki nahi aa raha. But then second I change the proportion. So all three gases are present. So 0 signifies 1 ppm and 1 signifies 2 ppm. So I change the mixture proportion and it analogously change up and down. So from that we can check okay it's also quantifiable mixture
From the amplitude.
from the amplitude. Then I plot the amplitude, all three gases the amplitude and get the LOD and all. So three gases at a time. Then so dynamic response of the sensor is repeatable or not. So what's the absorption time and desorption time? I just taken the experiment and this is selectivity curve. So these three gases are performing well, but xylene, formic acid, 2-propanol are in very low fashion. But this is also giving the response. It's not thinking, it's not giving the response. So we can extend the idea. If we have a particular interfacing circuit which is very noiseless, so we can detect these gases as well. So the sensor should be humidity should not be affected by the humidity, and that B is device to device variation. The stability is an issue with the AGH because silver is oxidized and it's changing the electronic configuration, so the device is not stable after 24 hours. So that's the limitation of this material. So I should choose the other material if the peak or the dip concept is true. Then same concept we can apply to the different materials. It should be by the physics. It should be there. It should be response as well. So this is a statistical study. Then comes to the interfacing circuit. Now my sensor able to detect three gases. Okay, although there is a stability issue, but yeah, three gases at a time. But most of the papers are reliable on the Wheatstone bridge configuration. Okay, one is reference, one is sensing, going up and down, and taking a response. But the V out in a form of what we are getting in a form of
changing resistance.
changing resistance. So this is the function of changing resistance. This is the Y. Function of changing resistance. But in my case, changing resistance is very less. Two peaks, there is not much difference. But if I able to do this or able to do this by the circuit itself, interfacing circuit, that हम peak detect कर सकते हैं, peak और dip, by using the peak detectors. So what is that? This is the I2 minus I1, मतलब this is the I gas minus I ref by I ref, which is equal to I gas by I ref minus 1. So this is giving me a peak or dip. If I can intact that function through the circuit, I can get the information. So by the giving the lectures with Professor TKB, the second year BTech, we have learned logarithmic block. So I e to power I by some neta Vt. From that we can derive the division by using this logarithmic block and the subtractor. We can divide the currents and this is intact. So one MTech fellow was working with me, Swapnil. So he was working on cadence and schematic. So with him,
So, and you also need other resistances, right? Like the previous one, like a Houston bridge.
no,
You need here
no.
other
In
resistance.
the best part is reference and sensor. We don't need any other resistance. So the sensor can be modulated like a reference current. Okay. And the another one is you can see the in the second.
So basically, you need here two sensors.
Two sensors.
One exposed, one not exposed.
One export, one.
But what is the guarantee that the response of two sensors would be identical?
No, no identical.
How
So-
that part is being taken care?
So इसको repeatedly examine किया है. So this is a fixed. ठीक है. I just do the delta I by I with the others resistance, मतलब other sensors, which is active. So ये वाला same ही है सबका. So this is there is sensor 1, sensor 2, sensor 3, sensor 4, sensor 5. So one base, one gas. Gas is one. So we can choose one base and try with the gas 1, gas 2, gas 3, sensor 1, sensor 2, sensor 3, or interchange. So I have checked. It's not neat identical sensors. So which is covered in my second enhancement type sensors presentation. There I elaborate the things more specifically. So these are the architecture, rail-to-rail architecture of the comparator, logarithm block, OTA, and this is the whole architecture. Symmetry in a cadence, SCL 120 nanometer. So
120 or only?
sorry, 180 nanometer. So for my circuit, okay, I have seen that my sensor is linear, but my circuit is also linear. So we have checked to varying the sensor's current from -9 nanoampere to milliampere. My output of the interface circuit is linear. This is the output of the sawtooth, which is used to change the PWM.
So you are changing this current by changing VD,
VG.
VG. But that will also change
No.
because
So
you need to vary keep on setting this VG, right,
Yes,
for the
yes.
peak detection.
yes.
Right. So should you do that or should you change the VD?
No. So this part is it's MEMS, it's not considered in a integrated circuit. So at that point,
No, don't do that.
I will remove it. At that point, we are varying from nanoampere to my sensor is giving current from nanoampere to milliampere. So beyond that, so sensor is a thing. So in this slide, you can see the sensor's current is varying. If I have chosen the TMDC or more conductive material, so microampere से वो milliampere में चला जाए. At that point, my circuit should be also.
Oh, you are saying that. Okay.
Yeah.
Okay, right.
And then this is a very interesting part. So this is I guess by I without guess mathematically. This is at the division point. This what we are getting at PWM by the PWM solving the duty cycle percentage. What we are getting. So our signature, our waveform is intact by the interfacing circuit. So, and that's the comparison with the other reported literature. So
You should write the year of publication.
yes sir, नीचे है मतलब
वो हम
reference.
आधा चौक में क्या?
ठीक है sir.
So write it side.
Okay.
Tell me about this reference for which year?
Reference for NDR.
Reference 50.
15.
First one, 2021.
2021. It's from our IIT only and PK Goel sir का paper.
और आपको बताओ 21 में benzene
21 में. So 21 में कार्बन बेस्ड FET बेस्ड सेंसर है तो डिटेक्शन द ppb लेवल बेंजीन एट रूम टेम्परेचर. So
is also 21.
it's also 21.
So latest 24, 25.
22 का लेटेस्ट है, 23 का लेटेस्ट है. नेचर कम्युनिकेशन का
Which one?
70. This one.
So they have not given any circuit anyway.
No circuit.
Voltage, why they have not given any voltage?
क्योंकि सर केमी रेजिस्टिव है एंड वो एलिवेटेड टेम्परेचर पे है 673 केल्विन.
That's not right.
Next one. Also, there is no cross gas analysis.
Oh.
Three or four gases
One
at a
gas.
time. There only one. So, but they are claiming that they can detect the 7 number of gases.
But they have shown.
No. Different chemical resistance.
Oh.
Different.
Different gas.
Yes.
Change the
Not-
materials.
Not
Change the
combined.
materials, not a
They have
single.
not combined.
So we are the only one single fact platform.
Single fact. तो Mayank, बाकी यहाँ पे जो है
Yes sir.
उसमें एक कुछ दिख रहा है मुझे जो 300 के रूम टेम्परेचर में 4 दिख रहा है, right?
Yes.
बाकी are higher temperature,
High
right?
temperature.
So if you just take those who have reported that 300 K
Yes sir.
sensing, so compared to that, what are the normality? Can you just say like 1, 2, 3?
So NDR the spectral method, it's a big optical thing. It's like उसमें gases जाएगा GCMC की तरह. Big chambers is there. Gas वहाँ पे जाएगा and optical detectors are there.
Optically detection.
So it's tabletop. It's bigger in
Okay.
size. The second one is gate polarity modulated. Number of gases is 1, but they are checked with the cross gases. But the voltage is minus 30 to 30.
So here gate polarity means they have also changed the sweep the gate.
Sweep the gate.
Okay.
But the operating range is very less, very high. And the second one is gate tunable single FET के साथ में use हुआ. But there is no LOD, there is no cross gas analysis, no circuit, and also higher operating range.
No, that is switching or you say gate polarity.
Polarity, sir.
That
Minus
means-
sweeping, the minus 40 to 40.
Sweeping is something polarity. So.
Nahin,
That
sir.
means you are either switch to -4 or plus.
No, sir. They are taking the whole.
Like you, like
yeah.
yours.
Yes, yes.
-5 to +5, they are doing it. So it's a continuous variation.
Continuous.
They have isolated the instance for multiple gas. They have done.
No, sir. Two gases. Yeah, two gases.
Two gas.
Who is the reference?
20. RCS example, it's more or less
Scheme. So
edged
Taiwan is
on
one.
Chinese.
ACS.
RCS, sir. RCS advances.
But you have done it for 3 gases.
3 gases.
Our target is to make 4 gases.
4 gases.
So Mayank, just one related question here. This operating voltage
Hmm.
that you were saying the plus minus 30. So
Plus minus.
that in this one plus minus 30 or plus minus 40 these are quite high.
Yeah.
So this depends on what?
So
This
the
voltage.
channel conductivity there is very less. कि वो current is not changing at a lower sweeping range. So उसको detectable range में डालने के लिए that's why they are increasing the VDS.
So it should be also the oxide thickness probably also.
Oxide thickness also.
Okay. Nice.
So that's my future work to more rigorously work on sensor and interfacing circuit, and The paper is submitted to the ACS Omega journal. This work, and
You have no paper published, I think one paper.
no sir, not published.
You have two papers in,
Yeah, in communication.
two papers submit.
Two papers submitted.
Where?
So the one is in ACS, and the second one is IEEE sensors.
Just later or since?
Sensors.
Census journal.
So journal. This was my previous published for references. Thank you.
Mayank, I have a question.
Yeah.
So you are using this, right? This circuit means you have this circuit for detecting that tip and this position, right? So if this circuit can detect, then do you still need the email part?
Yes, sir. So circuit is interacting the ML. Oh, sorry. Signature of the dips or peaks.
Okay, just finding the tip, and then it will be fed
Fed by the ML.
to the
Okay. At this part,
But email part you have not seen this part, right?
in this we are not. In the second presentation, I will show the ML
Email
part.
part. So are you going to for your second presentation now or after 1 month?
After 1 month.
Mike, what is the rule of pulse width modulation here?
So pulse width modulation actually, most of the microcontrollers work on digital scenario, digital analog to digital converter. So pulse width modulation is a technique which is noise which prevents the noise, and it's easy to handle. So what we are doing, we are just comparing with the sawtooth this voltage levels, and then checking the levels and comparing with the levels and the pulse width modulate.
No. Pulse width modulation is the duty cycle.
Duty
So
cycle.
on and off time will depend upon these upon what?
Upon the input what we are seeing in the at the division block.
But then this is not something to zero.
No.
So you must have a level. How do you choose the level?
So level.
Say suppose voltage starts with 0, it goes to V.
Yes, sir.
So then you want to make pulse width modulation of that.
Yes.
Duration of the on time
Yes.
depending upon the voltage level.
Yes, sir.
That is what you say.
Yes.
But that will be threshold, right?
Yes, sir.
So from V1 to V2, V low to V high.
V high.
So where is those?
So we here we
You
just
give a reference.
yeah
The
reference
base.
1.65 वोल्ट का हमने रेफरेंस रखा है.
उसका above जब होगा, how long this will be in above the pulse width
So
will be?
3 वोल्ट.
3.
3 to 3.2.
Up to that, just
हाँ. Yes.
and that gives you 1 0, like 3
1
volt, 0 3 volt.
Yes. So suppose this is a input.
Yeah.
So we are taking with
Yeah.
we are getting the pulses.
Pulse, yes. And pulse width is proportional to the voltage.
Volt.
We are above the threshold.
Above.
Width of the pulse will determine the amount of
Yes.
gas detected.
So then what will be the monitoring when you have multiple gases?
Yes, sir.
Then once is the deep or the peak. But how do you actually get the idea that this is for gas 1, this is for gas 2 or gas 3?
So that's the ML part.
No, from the VG. Our idea is that
Hmm.
gate voltage will vary, and for one gate voltage, for a particular gas, the sensitivity will be very high.
Yes.
That was the physics.
Yes.
So if we vary that, then if we give a ramp kind of a voltage, then we will get that kind of a spectrum.
Yes.
And where the peaking or dipping occurs, then that peak or dip will give you that for a particular gas.
Yes. So
that point is missing. I'm not understanding.
So by checking the only
Yeah,
ammonia.
here I understood.
Yeah.
But after you make your final PWM signal,
Yes, sir.
output, where this VG part is missing.
So,
Where you kept your VG?
I think we can just go to the next one.
So it is also another factor.
Oh, you put time. So
Yes.
is it this time related
So-
with the RAM?
yes.
So this time is related with that.
So what we are doing, we are sweeping the VGS here with the time and getting the response. So from VGS,
So what will be the best one, that you convert that time scale to the voltage scale?
yes, yes.
And then you plot it, and then mark that.
Okay.
That the deep is because of that gas.
Okay.
This is for that gas. This
Yes,
is for
yes.
that gas. Then from there you are now going into the ML channel.
Yes.
AIT. So
Yes.
that is this for huge number of gases or huge
Yes.
monitoring. Then you need that machine learning.
Machine.
Now I am doing it for a known case. For
Yes.
unknown case, the pattern. will
Pattern.
be, learning, reinforcement.
Be careful. There might be some delay.
Yes.
Right,
There will be.
of
We
this
have to-
processing.
we have to-
So
yeah.
take care of those delay in synchronizing
Synchronizing.
this. So suppose then man here you are getting a dip at a time 0.03 second,
Hmm.
which say corresponds to say plus 3 volt.
Plus.
Say plus 3 volt. And which corresponds say one such gas,
Yes.
gas A.
सेम हम वही किया. So 0 to -5 के
Okay.
बीच में हमारा वो आ रहा था.
Right.
We are
So
getting the
consider this as plus 3.
Yes.
Then suppose now you have all three gases.
Hmm.
Then in this plot you will also expect one peak at 0.03, one probably at 0.01 and the other one probably at 0.04.
Yes.
So three peaks simultaneously.
Simultaneously.
So is it the same thing like the where you are getting the dip here it should also get a dip, or you will
Yes,
get
yes,
only
yes.
the peak?
No, dip and peak both.
Dip and peak.
So the circuit should be able to give the peaks and dip both. So if I choose directly the peak detector, they are giving the highest peak. वो dip नहीं दे. So that's why the logarithmic block what we have designed the best performing thing. So many things we can read.
Right. But my what if the scenario है कि suppose like go back. Please yes. One more that signal here. For example, you see this now next one. Next. Yeah. See this figure B. Right. This here, for example, as the currents are not very high, so many times we will also see some type of noise. So this type of noise, right? Do you think that please, I mean, I do not know whether you have checked or not whether this noise affects the performance of the circuit or not.
हाँ, वो perform हुआ है.
वो थोड़ा देख लेना.
वो yes. So वही next उसमें यही है. So what the noise compensation, the sensitivity enhancement, temperature compensation, because in right now in what we are present is not temperature compensating. So band gap preference biasing, the chopper stabilization, so many things we have to add. So simultaneously sensors and the circuit and the ML part is going on.
For the first part, I have one observation is that your ramp rate.
Yes, sir.
So there should be a relationship with your rise time and the recovery time.
Yes, yes.
So your ramp rate have you considered? Because it is almost like a quasi-static process.
Yes, sir.
You cannot do it very fast. You need some time to charge up and charge to, because it's a fit.
So what we have done?
Considering your millisecond time, how do you optimize that amping?
So we have seen the response time is approximately 3 seconds. It's for 5 seconds. It's 2 seconds. So what we did, we filled the chamber at 30 seconds because the sensor is got approximately saturate after 5 seconds. ठीक है, तो उसको मैं 30 seconds के लिए fill करके रख दिया. I just kept fill and then take the reading. Take the sweep -5 to 5 because I am sure my sensor is in saturation mode. All
That is a very good question, sir.
dynamics what we have.
So it is related to man. Please go to one of the sensor characteristics, like where you are varying the voltage, now peak, right?
Yeah.
So here, na, have you checked? Suppose sensor is saturated, right? Now you are varying this VG Like this sweep rate may also affect the
Yes,
performance
yes,
of the
yes,
circuit.
yes.
So I do not know whether you have checked or
No,
not.
not checked.
So please do one step. Huh? Please change this.
Sweep rate.
Sweep
Because
rate.
हम वो -5 to 5 बस click करते हैं and then getting the results.
Yeah, no, you have to introduce delay.
Delay.
Right. Manual delay you need to introduce and then check the
Hmm.
how it is affected.
Overlapping.
Overlapping.
The recovery time is normally slow
Yes.
than the
Response time. That's why I just fill the chamber and then take the reading.
Please make a detailed study on the RAM.
Yes, sir.
Please find first part.
Yeah.
ठीक है, that's good. So people can go and
Yes, sir.